Hello everyone. The first humans to reach Mars may never see Earth again, not because they would not want to return, not because of a simple malfunction, not because a rocket engine fails at the wrong moment. The reason is colder than emotion and harsher than luck. It is fundamental, mathematical, physical, because returning from Mars is not like boarding a flight home from a vacation. It is the most complex engineering challenge humanity has ever seriously considered. A survival problem where physics works against you at every turn. Most stories about Mars missions focus on the heroic part, planting a flag, touching the red soil, building a new outpost. But the darkest part is usually skipped. Going there is the easy part. The nightmare begins when you try to come back. And when you understand why coming back is close to impossible, you realize something else as well. We are not nearly as ready as we like to pretend. If you want to face these cold, quiet truths, if you want to let your mind open into the deeper mysteries behind the headlines, then stay with this journey. If you haven't already, you can consider subscribing to the channel and liking this episode. Your support helps these silent realities reach more curious minds. Now clear your mind, lean back. We are going deeper. Pause. Everything begins with a concept that looks deceptively simple: distance. On paper, Mars is about 225 million kilometers from Earth on average. But in space, average is a mirage, because neither Earth nor Mars is ever still. They move constantly around the Sun on different orbits at different speeds. Sometimes, in a rare alignment, Mars comes relatively close, about 55 million kilometers. It can feel like a neighbor across the street. Other times, Mars swings far away, to the other side of the Sunday, and the distance can exceed 400 million kilometers. That changing separation creates what engineers call launch windows. These windows are not convenient schedules. They are narrow, unforgiving opportunities, like doors opening in the sky. And they open only about once every 26 months. If you miss the window, you wait more than 2 years for the next one. That means a Mars traveler cannot simply say, "I'm scared, I want to go home." Not in any immediate way. The universe does not care about your fear, your regret, or your longing. Planetary alignment does not respond to human emotion. Once you arrive, you are trapped by orbital mechanics. For roughly 2 years, Mars owns you. Your return ticket depends on the geometry of the solar system, not on your will. Pause. Even the journey there is a kind of psychological and biological experiment. With current propulsion technology, a trip to Mars takes about 6 to 7 months, sometimes longer. That is more than half a year inside a metal capsule smaller than a studio apartment. For months, the same walls, the same air, the same voices. No privacy, no escape. And the view outside the window changes in a way that quietly breaks the mind. At first, Earth is huge, blue, bright, comforting. It feels near. Then, day by day, it shrinks. It becomes a marble, then a bright star, then, eventually, a pale speck trembling in endless darkness. This is not only physical distance, it is a severing. Astronauts on the International Space Station can always look down and see Earth, oceans, clouds, continents. Home is right there. That visual bond matters. It anchors the mind, but Mars travelers lose that anchor. Earth stops feeling like a place. It becomes an idea, a memory, a concept. From hundreds of millions of kilometers away, all of human history, every city, every war, every love story compresses into a point of light, and you are outside of it. Pause. While you drift through that emptiness, physics begins a quiet war against your body. Your muscles weaken even if you exercise. Your bones lose density without gravity. Calcium leaches into your bloodstream. Even your vision can be threatened. In microgravity, fluid shifts upward into the head. Pressure changes inside the skull. This can distort the shape of the eyeballs and stress the optic nerves, a condition known as spaceflight-associated neuroocular syndrome. It can leave lasting visual damage. You might arrive at Mars after months of travel and discover that you can't see as sharply as you used to. You may finally reach the planet you dreamed about and see it through blur. Pause. But you arrive. You descend toward the red world. Photos are taken. Statements are recorded. History is written. And then the engines shut down. The dust settles. The first excitement fades, and a different reality moves in. Because Mars is not a new home. It is a dead planet that will try to kill you in every possible way. Its air is toxic. Its soil is chemically hostile. Its surface is washed in radiation. And the cruelest part is this: the fuel you need to return is not waiting for you. In fact, the fuel requirement is so enormous that you cannot realistically bring it with you. Landing on Mars is one thing. Leaving Mars, climbing out of its gravity well, reaching orbit, and then crossing interplanetary space back to Earth is another monster entirely. The math is already whispering the same message. The return is not just difficult, it may be near impossible. Pause. And even before you touch the ground, the journey itself is often misunderstood. Many people imagine travel as a passage, a brief discomfort between two destinations. But a Mars transit is not a short commute. It is prolonged confinement. It is monotony so intense it becomes physical. 6 to 9 months of being packed into a capsule. No fresh air, no open space. And during that monotony, a silent enemy passes through your ship as if the walls are not there. That enemy is radiation. On Earth, we live under protection. Our magnetic field deflects many dangerous particles. Our thick atmosphere absorbs the rest. But the moment you leave Earth's shield, that protection ends. Deep space is filled with high-energy particles, galactic cosmic rays, solar energetic particles. They pass through metal like bullets through thin fabric. They strike your cells. They damage DNA. They alter tissues. For a Mars transit, estimates often place exposure around 0.66 sieverts for the trip outward alone, depending on conditions and shielding. Numbers can feel abstract, but the effects are not. This is not a mild inconvenience. It is a steady biological assault, and it is not only about cancer. In mid-2024, a major line of research drew attention to another danger, long underestimated: kidney damage. Radiation in deep space can cause lasting changes to kidney tissue. It can increase the risk of kidney failure. If kidneys fail during the mission, there is no dialysis machine, no transplant, no rescue. In space, organ failure is not a hospital emergency. It is the beginning of a slow, inevitable ending. Pause. Meanwhile, microgravity continues its work. Weightlessness feels fun at first. It feels like freedom. But long-term, it is a trap. The human body evolved under gravity. It built strength to resist constant load. When that load disappears, the body makes a ruthless decision. It begins shutting down what it thinks it no longer needs. Bones can lose around 1 to 2% of density per month. Muscles atrophy. Coordination declines. Calcium, released from bones, increases the risk of kidney stones, which is not what you want when radiation is already stressing your kidneys. And the fluid shift toward the head increases intracranial pressure. Eyes flatten. Optic nerves can swell. Your body becomes weaker. Your senses become less reliable. And your mind is being pushed toward isolation. Because Earth is fading, pause. At last, Mars grows large in the window, a red sphere, rust-colored, ancient, silent. But arriving at Mars is not the same as landing on Mars. Those are two completely different problems. In space, you are drifting. In space, you are safe in a certain way. The moment you commit to landing, you meet Mars's most cruel engineering paradox. Its atmosphere is too thin to help you, but thick enough to hurt you. On Earth, a spacecraft can use the atmosphere like a braking cushion. Air resistance slows you down. On Mars, the atmosphere is about 1% of Earth's surface pressure on average. It provides very little aerodynamic braking for a heavy craft. It is almost like there is no atmosphere, and yet it is still present enough to generate intense heating during entry. So it won't slow you effectively, but it can still burn you. That is the paradox. For robots, we have managed it barely. Even landing a 1-ton rover was extremely difficult. The Perseverance landing was called 7 minutes of terror for a reason. It required a chain of events to go perfectly. Now imagine landing not 1 ton, but tens of tons. A human mission does not bring only a person. It brings life support, habitat modules, supplies, tools, spare parts, power systems, machines to produce fuel. Depending on the architecture, you may need something like 50 to 100 tons of mass delivered to the surface. And this is where the math becomes merciless. The landing systems that work for small payloads do not scale easily. Parachutes become too large and too fragile. The thin air cannot inflate them effectively at the required speeds. Airbags are limited. Sky crane systems are not built for truly massive loads. So you rely on retro rockets. But rockets need fuel. Fuel adds mass. More mass requires more fuel. More fuel adds more mass. It becomes a spiral. Engineers have known this for decades, and there is still no single, proven, fully validated solution for safely landing large human-class payloads on Mars. If you cannot slow down, you do not land. You impact. You become a crater. Pause. But suppose a miracle happens. Suppose new technology emerges. You solve entry, descent, and landing for a heavy system. You touch down. The engines cut off. You step onto Mars. For a moment, you might feel triumph. And then the trap closes. Because now you are on the surface. And the surface is where the return problem becomes brutal. Mars is far from everything that keeps humans alive. No hospitals, no workshops, no supply chains. And the most immediate truth is this: your tanks are empty. The fuel that brought you here is not the fuel that can take you home. This is not a car trip. You cannot refuel on the roadside. The nearest gas station is Earth, a pale dot in the sky. Pause. Here, the logic becomes almost unbearable. To return from Mars, you need enormous amounts of propellant. Numbers vary by mission architecture, payload, and technology. But in many classic human mission concepts, total propellant requirements become massive. What matters is the core reality. You cannot bring everything from Earth. Because to carry return propellant, you need more launch mass, which requires more fuel, which increases mass again. It spirals quickly beyond practicality. So the only way home is to make fuel on Mars. To produce it there, from local resources, from dust, air, and ice. And Mars does not hand you those resources. You must extract them, refine them, and transform them in a hostile environment. This is where the romantic Mars story turns into industrial nightmare. Because returning is not a single rocket launch. It is a full-scale chemical manufacturing operation on another planet. Pause. The most famous proposed solution is based on an old chemical process, the Sabatier reaction. On paper, it is elegant. Mars's atmosphere is mostly carbon dioxide, about 95% CO2. CO2 is poison to breathe, but it is useful chemistry. If you take CO2 and combine it with hydrogen, you can produce methane and water. Methane is a rocket fuel. In simple terms, you turn alien air into fire. Modern alchemy. But the equation has a missing half. Hydrogen. Mars's atmosphere has almost no hydrogen. So you must bring hydrogen from Earth or obtain it from Mars. Bringing it is difficult. Hydrogen is light, but storing it is hard. It leaks. It requires special tanks. Often, it must be kept extremely cold. It takes volume, and volume means larger systems, larger mass, larger complexity. So many plans rely on the other path. Find water ice on Mars, extract it, and split it into hydrogen and oxygen. That is not a simple task. It is mining. It is heavy industry. It is long-term reliability under radiation, cold, and dust storms. You would need pumps, separators, compressors, cooling systems, high-pressure tanks, and they must operate for months or years with minimal failure. On Earth, even the best industrial plants require constant maintenance. Parts wear out, filters clog, valves seize, seals degrade. On Mars, there is no spare parts store, no technician team arriving tomorrow. If a critical component fails, your fuel production stops. If fuel production stops, your return becomes impossible. Mars fuel production is not a science experiment. It is a life or death manufacturing chain. Pause. And for safety, it is not enough to land and then start producing fuel. You cannot arrive and hope. The fuel must be ready before people land. That implies robotic missions that arrive first, set up the system, and fill tanks, so that when humans arrive, the depot is full. But robots fail. Dust accumulates, power drops, software glitches, mechanical parts degrade. A global dust storm can cut solar input for months. If a robotic fuel plant fails before humans arrive, then humans arrive to empty tanks, to dead machines, to silence. And if the tanks are empty, the future is empty. Pause. The hydrogen problem leads you to the most difficult resource on Mars: water. Mars does have water ice, but it is not lying around in convenient lakes. Because Mars's low atmospheric pressure does not allow stable liquid water on the surface, water is trapped as ice beneath the ground or locked into minerals. To reach it, you must drill. And Mars is not a soft beach. The surface is a hardened layer of rock and regolith, shaped by billions of years of cold and impact. Ice can be meters down, beneath a crust that can behave like frozen concrete. You need robust drilling equipment, industrial-grade systems, and you need them to function in remote conditions. But there is a deeper challenge. Humans cannot arrive first and then slowly start digging. Fuel production must happen before human arrival. That means robots must drill, extract, and process water ice autonomously for long periods, with no on-site maintenance. On Earth, drilling breaks bits, motors burn out, pipes jam, humans fix it. On Mars, your robots must work in extreme cold with abrasive dust for years. And the dust is not harmless. Mars regolith contains toxic compounds such as perchlorates. Perchlorates are dangerous to humans and chemically harsh to equipment. They can be corrosive. The fine dust gets into seals. It grinds surfaces. It clogs moving parts. Mining becomes a slow battle against abrasion and failure. And even if you reach the ice, you must melt it. Melting ice on a freezing planet requires a lot of energy. So the water problem turns into a power problem, and the power problem turns into another trap. Pause. Energy on Earth is easy to take for granted. Flip a switch, lights turn on. But on Mars, energy is fragile. It can be rarer than water. You need power for everything: life support, heating, air circulation, water extraction, electrolysis, fuel synthesis, communications, lighting, computers, repairs. Where does it come from? The obvious answer is solar power. But Mars is farther from the sun than Earth. Sunlight is weaker, and Mars has something that makes solar power feel like betrayal. Global dust storms. These storms are not like local weather. Sometimes they expand until they engulf the planet. They can last weeks, sometimes months. During such storms, sunlight at the surface can drop dramatically. Panels become useless, and dust does not merely block light. It coats surfaces. Mars dust is electrostatically charged. It clings. It sticks to panels, radiators, seals. It is stubborn. In 2018, the Opportunity rover was effectively killed by dust storms. Its solar panels could not recharge. Its batteries drained. It went silent. For a robot, that is a sad ending. For humans depending on electricity for oxygen and heat, it is a death sentence. So planners turn to nuclear power, stable power that does not depend on sunlight. But nuclear systems are heavy. They require shielding. They require safe cooling. They add risk. If a reactor fails, you cannot call a specialist. If it leaks radiation, you may have nowhere to go, because going outside is not safe. Outside is lethal, and inside might become lethal too. Energy becomes not just a technical problem, it becomes psychological siege. Imagine being inside a habitat during a global dust storm. Outside, the world disappears. The sky becomes a rust-colored darkness. You cannot go out. You cannot explore. You reduce power consumption. Lights dim. Heat lowers. Days blur into each other. You listen to wind and dust hammer the structure. You wait, and you do not know when it will end. If your power system fails, you do not die instantly. You die slowly. Temperature drops. Air circulation weakens. Water processing slows. Food production declines. Fuel production stops. And if fuel production stops, you miss your launch window. If you miss the window, you wait another 26 months. And every additional day on Mars is another day your odds shrink. Mars turns time into a weapon. Pause. Then there is the silent enemy that is always present, even without a global storm. Dust. Mars dust is not like Earth dust. On Earth, wind and water round particles over time. Sand becomes smoother. Mars is dry. Water has not worn the dust down. Under a microscope, Mars dust can look like sharp fragments, like broken glass. Particles can be only a few micrometers across, smaller than a human hair by far. And because they are electrostatically charged, they cling to everything. They stick to suits, visors, gloves, tools, seals. Cleaning them is extremely difficult, and the problem is not cosmetic. Dust gets into moving parts. It grinds joints like sandpaper. It eats at seals. It compromises the integrity of spacesuits. Every EVA, every step outside, wears down your suit. A suit is not clothing on Mars. It is a wearable spacecraft. A small tear can be fatal. Dust also infiltrates habitats. No matter how careful you are, each entry brings dust inside. In a sealed environment, it accumulates. And Mars dust is not only abrasive, it is toxic. Perchlorate salts can disrupt thyroid function and harm health over long exposure. The dust can irritate lungs. It can create chronic disease. The planet tries to get inside you. Dust also attacks electronics. It coats solar panels. It blinds sensors. It clogs radiators. On Mars, technology is not used in harmony with nature. It is used against nature, and nature does not negotiate. Pause. Now consider breathing. On Earth, breathing is effortless, a reflex you do not think about. On Mars, breathing is a paid privilege. The atmosphere is mostly carbon dioxide. It is poison. But the greater danger is pressure. Mars has about 1% of Earth's air pressure. If you step outside without protection, you do not simply suffocate slowly. The low pressure causes a catastrophic failure of normal biology. You would lose consciousness quickly. Body fluids can begin to boil at body temperature under low pressure. This is known as ebulism. Mars offers no mercy. So, living on Mars means living inside pressure vessels, inside metal, inside glass, inside systems. Your life depends on seals, valves, compressors, sensors. One failure can be lethal. Even inside, you cannot relax because the environment is always waiting. If a habitat loses pressure, the outside vacuum does not push away. It rushes in. Mars does not forgive mistakes. Pause. Even the dream of a self-sustaining habitat hides traps. People imagine a closed loop. Humans breathe out carbon dioxide. Plants absorb it. Plants produce oxygen. Humans breathe oxygen. It sounds perfect. But closed ecosystems are unstable. If plants produce too much oxygen in a sealed habitat, oxygen levels can rise into dangerous territory. Fire risk increases. To reduce oxygen, you must vent air. But venting loses precious buffer gases as well. In many designs, nitrogen is needed to maintain safe pressure and breathable composition. Mars does not provide easy nitrogen replenishment. So you face a balance that must be controlled precisely. Too much oxygen is dangerous. Too little oxygen is deadly. On Earth, the atmosphere is a vast, stable buffer. On Mars, your atmosphere is a machine state. A sensor error can become a catastrophe. A fan failure can become suffocation. A clogged filter can become poisoning. Breathing becomes an engineering problem that never rests. Pause. Now we return to radiation. Because radiation is the enemy that cannot be sealed out easily. Earth's magnetic field is a shield. Mars lost most of its global magnetic field long ago. It has no strong planetary defense. So radiation reaches the surface far more intensely than on Earth. Even inside habitats, shielding is limited by mass. To shield well, you need dense material. Dense material is heavy. Heavy material is expensive to launch and difficult to land. Water can shield radiation, but water is precious. Regolith shielding is possible berry habitats under soil, but that helps mainly on the surface. It does not protect you during transit. And transit is long. It is months of exposure, twice, plus time on the surface. Radiation doesn't merely raise cancer risk. It can accelerate vascular damage, cognitive effects, immune suppression, and, again, kidney damage is a growing concern. In the simplest, coldest summary, you cannot undo radiation dose. You can only reduce it or accept it. A Mars mission becomes a biological gamble. Pause. Now add another layer. Gravity. Mars' gravity is about 38% of Earth's. At first, this feels like power. You jump higher. You feel lighter. but your body interprets it as permission to weaken. Bones lose density, muscles shrink. The heart adapts to lower demand. On Mars, this is adaptation. But if you ever attempt to return to Earth, the adaptation becomes a trap, because Earth's gravity will feel crushing. A body tuned to Mars may struggle on Earth. And after long exposure to low gravity plus microgravity transit, some damage may be difficult to reverse. The nightmare scenario is simple. You return physically to Earth, but your body cannot function there anymore. You survived Mars, but Earth becomes unlivable. Not because Earth changed, but because you did. This creates a paradox that sounds like science fiction, but is grounded in physiology. A Mars mission can become biological exile, not only by rockets, but by your own altered body. Pause. And then there is vision again. Astronaut eyes are not a minor issue. In spaceflight, vision changes have been documented. The fluid shift to the head increases pressure. Eyes flatten. Optic nerves can swell. Blind spots can develop. On the ISS, some astronauts returned needing corrective lenses. On Mars, mission durations are far longer. 3 years is not unrealistic when you include travel out, surface stay to catch return window, travel back. If neuroocular changes accumulate, you might face lasting impairment. And in the mission where reading instruments and spotting hazards is critical, impaired vision is not an inconvenience. It is a hazard for you and for everyone relying on you. Pause. Now consider medicine. On Earth, illness is buffered by a massive safety net. Hospitals, imaging machines, surgeons, blood banks, sterile operating rooms. On Mars, there is none of this. You can carry only limited drugs, limited equipment. Even simple conditions can become lethal. Appendicitis on Earth can be a routine surgery. On Mars, it can be fatal. If the appendix ruptures, infection can spread quickly. Sepsis can kill without advanced care. And who performs surgery? You may have someone with medical training, but likely not a specialized surgeon. Mass and staffing limits prevent bringing every specialist. So, a pilot or engineer might become the person holding a scalpel, not in a surgical theater, but on a table in a habitat, with limited sterility, with dust infiltration, with reduced gravity changing fluid behavior. Blood does not drain the same way at lower gravity. It can pool. Droplets can float and spread contamination. Even bacteria can behave differently in space environments. Some evidence suggests increased virulence or resistance in microgravity conditions, and the patient's immune system may already be compromised by stress and radiation. So even if the surgery works, infection risk is enormous. There is no ICU, no advanced life support. A medical emergency on Mars is not a problem to solve with skill and equipment. It is often a countdown. And because Mars is far, Earth cannot help in real time. Communication delay, depending on planetary positions, ranges from minutes to more than 20 minutes one way. That means 40 minutes round trip. Houston, we have a problem, is a movie line. On Mars, by the time Earth hears you, the crisis may be over, either solved or fatal. You are alone, when it matters most. Pause. And if someone dies, the problem becomes even darker. On Earth, death is surrounded by rituals: burial, cremation, funerals. On Mars, those rituals collide with physics. You cannot easily dig a grave. The ground can be frozen and hard. Digging is dangerous and labor-intensive in suits. Cremation would require oxygen and energy resources needed for the living. Returning a body to Earth is unrealistic. Space is limited. Decomposition in a closed environment would be dangerous. The cold logic pushes you toward a horrifying solution. Using Mars as a natural freezer, the outside environment is cold and dry. It can preserve a body. A body can be placed outside, sealed, and left. But psychologically, this is devastating. That person does not fade away into Earth. They remain, a frozen presence outside your habitat, a silent reminder. And if the death involved disease, the fear grows. Is the cause still inside our air system? Inside our water loop? Death on Mars is not only grief, it is logistical terror and psychological damage. In a closed habitat, trauma has nowhere to escape. It echoes. Pause. Now we reach one of the most underestimated threats: silence. Not just acoustic silence, but communicative silence. On Earth, we expect real-time conversation. We speak and receive immediate responses. That immediacy supports relationships. It supports emotional regulation. Mars destroys immediacy. Signal delay kills dialogue. If you ask, "Are you okay?" you wait. Minutes. Sometimes more than 20 minutes for your words to arrive. Then another long wait for an answer. 40 minutes of emptiness for a single exchange. It's not a conversation. It's sending messages into a well and listening for echoes. In emergencies, this is lethal. Earth cannot guide you in real time, cannot react in time. The control center becomes an audience watching the past. Your present is their delayed feed. That knowledge creates a constant psychological pressure. Whatever happens, it happens without rescue. Even emotionally, the delay matters. A loved one's "I miss you" arrives late. Your reply arrives late. You end up speaking to the past version of your family, always out of sync. The feeling of shared time begins to fracture. Slowly, Earth becomes less like a living relationship and more like a memory archive. Pause. Long-term isolation has patterns. We have studied it in Antarctic stations and submarines. One of the most dangerous phases is called the third quarter phenomenon. Not the start, when excitement is high. Not the end, when return is near. But the middle, when novelty dies and the finish line feels distant. That's when morale collapses. Habitat life becomes repetitive. Same schedule, same meals, same corridors, same faces. No private place to disappear. Small irritations expand into serious conflict. A sound someone makes while eating, a habit, a repeated joke. Under confinement, these become unbearable. Groups form, tension rises, trust erodes, and trust is not optional on Mars. You depend on each person for survival. If social cohesion breaks, safety breaks. And in a system where a mistake can kill everyone, psychological breakdown is not just sadness. It is mission failure, possibly catastrophe. Pause. One of the strongest psychological anchors in space is the view of Earth. Astronauts on the ISS look down and see a huge living planet. They see weather systems. They see lights at night. They see home. This supports the mind. But Mars travel breaks this anchor. At first, Earth is big. Then it shrinks. Then it becomes difficult to distinguish. Then it disappears into background stars. This is sometimes described as an Earth out of view phenomenon, a moment when the planet that defines your identity is no longer visible. For some minds, this can trigger dissociation, a feeling that home is not real, that life on Earth is dreamlike, that your memories are distant stories, not lived reality. Even on Mars's surface, Earth can be hard to see. And when you cannot find it in the sky, a deep loneliness opens. Not just loneliness from people, loneliness from the entire human world. You are standing on a dead planet, looking into a sky where your species' home is invisible. That is not a normal human experience. Pause. Now consider something even darker. Children. Many visions of Mars colonization show families under domes, kids running, a new society. But a child born on Mars would be part of the harshest experiment imaginable, because human development is shaped under Earth gravity. Cell division, bone formation, muscle development, cardiovascular systems, all tuned to 1G. On Mars, gravity is only 38G. We do not fully know what a fetus developing under that condition would become. We can predict trends: lower bone density, different muscle development, different cardiovascular adaptation. A Mars-born human might be perfectly adapted to Mars, but unable to live on Earth. Earth gravity could crush them. Their bones could fracture under their own weight. Their hearts could struggle to pump blood against stronger gravity. Breathing could feel like lifting weight. This creates an ethical cliff. We imagine colonization as freedom, but we might be creating biological prisoners, children who can never visit Earth. For them, Earth becomes a forbidden world. They can see it in images. They can hear stories, but they may never stand there. Some scientists have even speculated on long-term divergence, a branch of humanity shaped by different gravity and radiation, a future where Mars humans are physiologically distinct, not by ideology, but by physics. A prison made not of bars, but of gravity. Pause. Because of these barriers, some mission planners have proposed a chilling solution: one-way missions, Mars stay missions. They avoid the return problem by removing it. No return fuel, no return vehicle, no return risk. Just get people there and keep them alive as long as possible. It sounds mathematically neat, but ethically, it is heavy. Sending someone to a planet with no possibility of return is not exploration in the old sense. It is voluntary exile, or something close to it. On Earth, it is easy to say yes in a warm room. I would do it. I would give my life. But can anyone truly consent to an experience they cannot imagine? Years of isolation, Chronic radiation exposure, constant danger, the psychological weight of regret with no escape. If one day you wake up and want to go home, the answer is simply, you cannot. One-way missions can become a confession of technological weakness, a way of turning an engineering failure into an ethical choice. We can't bring them back, so we won't try. That trade does not solve the problem. It relocates the problem into human suffering. Pause. Even the dream of a self-sustaining colony faces cruel arithmetic. Closed ecosystems are delicate. Machines degrade. Parts fail. Entropy wins. Studies modeling hypothetical Mars colonies have pointed to destabilizing feedback loops. Food production, gas balance, pressure control, each depends on perfect operation and maintenance. On Earth, systems survive because support is infinite. Supply chains exist. Replacement parts exist. Specialists exist. On Mars, every part has to be brought, stored, or built. 3D printers can produce some components, but not everything. Not complex electronics. Not all high-performance materials. As parts fail, colonists cannibalize equipment. They take parts from one system to save another. The habitat becomes a machine eating itself to live. Eventually, the systems degrade past recovery. Lights fail. Air circulation weakens. Temperatures drop. Plants die. And the colony becomes a metal tomb on the red surface. Not with a dramatic explosion, but with a slow, cold extinguishing. That is how Mars kills. By time, by depletion, by the inevitability of failure in a closed environment. Pause. Now, return to the original point. Why might the first humans on Mars never see Earth again? Because return is not a single action. It is a chain of miracles. You need the right launch window. You need heavy landing success. You need survival infrastructure. You need continuous power. You need water extraction. You need hydrogen production. You need fuel synthesis. You need storage. You need a launch vehicle. You need reliable health over years. You need enough bone and muscle to survive re-entry and Earth gravity. You need luck with radiation. Break one link and you do not return, and the universe does not provide spare links. Pause. Even if you make it back, the return is not a victory parade. It is a painful epilogue. After Mars, your body is not the same. Transit back is again months of microgravity, more bone loss, more muscle loss. Then Earth re-entry loads you with intense G-forces. Your weakened cardiovascular system must survive it. You may land alive, but unable to stand. On the ISS, astronauts return after 6 months and struggle to walk. A Mars mission could mean years of altered gravity plus radiation. Recovery might take years. Some damage might be permanent. Vision changes. Bone density loss, cardiovascular decline, and radiation damage that cannot be undone. Cancer risk increases. Cognitive effects may appear later. The return can feel like returning to a planet where your body no longer belongs. And socially, Earth has moved on. Years passed. People aged. Life changed. You return to a world that continued without you. and you return changed. Mars does not simply test technology. It rewrites people. Pause. At this point, a hard question appears beneath the engineering. Why send humans at all? If the goal is knowledge, data, understanding why risk fragile biology, we already have explorers that do not need oxygen. They do not need warm habitats. They do not fear radiation. They do not suffer depression or isolation. Robots, rovers like Curiosity and Perseverance, are already on Mars. They do not complain. They do not get cancer. They do not lose bone density. They endure. They gather data. They send it home. And as AI improves, robots become even more capable. They learn. They adapt. They navigate autonomously. They see in wavelengths human eyes cannot see. They process more data than a human mind can handle. There is also an intermediate option: telerobotics from Mars orbit. Humans stay in a safer spacecraft, reducing surface exposure and avoiding the hardest landing problem. They operate robots on the surface with minimal delay. They work as if present, without standing on toxic ground. This reduces risk and cost. Yet the human dream persists. Footprints. We want our bodies there. Sometimes that desire is less science and more pride. But Mars is not a mountain. The cost is not money alone. It is human suffering. And suffering becomes morally heavier when alternatives exist. Pause. Mars has been there for billions of years. It is not going anywhere. It waited through the rise and fall of life on Earth. It can wait longer. The universe does not share our impatience. It teaches slow lessons. Sometimes the wise move is not rushing forward. Sometimes restraint is progress. Because waiting is not failure. Waiting can be respect for the boundary between what we want and what physics allows. Pause. Now, as we come toward the end of this story, let the noise of rockets soften. Let the countdown fade. Let the metal and the alarms drift away. Because you do not have to take that journey tonight. You are on Earth, the safest harbor we know. Feel the place where you are lying. Your body is held by a familiar gravity, not too weak, not crushing, steady, a gentle pull that says, you are home. Notice your breathing. The air entering your lungs is not manufactured by a machine. No oxygen computer adjusts it. No filtration system fights toxic dust to keep you alive. The atmosphere is simply there, waiting for you, made for you by billions of years of planetary processes. You breathe without fear, without calculation, without monitoring. Pause. In your mind, the red desert can remain distant. The 40-minute communication delays, the endless storms, the radiation rain, the machinery that must never fail. All of it can stay far away. You are here, in a warm room, protected. Your muscles can relax. Your shoulders can drop. Your jaw can unclench. You are not trapped in a capsule. You are not sealed into a habitat. You are not counting watts and oxygen. You are allowed to rest. One day, humanity may reach Mars safely. Not just reach it, but return. When technology can truly protect biology, when systems can fail gracefully, when redundancy is real, when life support is not a fragile chain. Until then, the smartest exploration may be the kind that does not spend human lives. We can explore with machines. We can explore with telescopes. We can explore with dreams. Because dreams travel farther than rockets. Dreams ignore launch windows. Dreams do not need fuel. Dreams return effortlessly. Pause. Now let your body sink deeper into the bed. From your toes to your calves. From your thighs to your hips. Let the weight feel safe. Let it feel like permission to stop holding tension. Let your chest rise and fall naturally. Let the mind's images fade like distant lights in space. If thoughts come, let them pass. Like dust drifting in a beam of sunlight, the universe will keep moving without your effort. Mars will keep waiting. Earth will keep turning. Stars will keep burning. And you can sleep. Let the world carry you. Let time slow down. Let the story dissolve into quiet, sweet dreams.